Okay. Hi, good morning, everyone. For those of you who've lasted to day 3, early morning. Okay, so today what I want to show you is how we tie together all these elements of the model, of the modeling, and the extraction of the fundamentals in terms of the physics that matters for the black hole growth problem, right? So today I want to show you how we've tied it together. And so essentially, I want to show you how we constructed the models. You've seen all the elements that have gone in, so I'll go over those briefly. And then I'll show you the implementation and the interpretation and the results. So I just wanted to alert everybody that, since these were pedagogical lectures, I wasn't giving you references everywhere, but on here, I have a list of all the people who've been working on various aspects of the problem, especially last 10 years have been really, really active. So once again, I have a little bit of introductory stuff which I'll just go over very quickly with the observational data, the various pieces of observational data that go into the model. And the question is, some of the pieces of observational data go in as constraints, and some are going to be the data with which we are going to match our predictions for the model. So there's a difference between which bits we are going to use as input constraints and what are going to provide our benchmark for calibrating the models that you actually produce. So this is a rough outline. I'm going to try my best to maybe go a little fast, but get through to the end because I really would like to wrap it up nicely. So we've seen this already. We've seen that there's more likely a fundamental way in which black holes and their supermassive black holes and their host galaxies are connected. So this, as I told you, and this energetics of the feedback. So the big questions that we have, and I think I've been phrasing them as we went along, and so here they are all put together, which is the sort of observed correlations give you some kinds of scaling relations that give you a starting point for building these models. And the question is, when are these correlations set up, or how fundamental are they? And then in the modeling, as I mentioned to you already as well, that there's a real interplay between initial conditions, which is seeding, and the growth history, which is the accretion models, what we assume for the accretion geometry and so on, and the dynamics of black hole mergers. Because basically black holes are going to grow, as I mentioned before, by 3 processes. So they're going to grow by direct accretion of gas. They're going to grow by mergers, actual mergers of black holes that happen when galaxies, halos merge, dark matter halos merge, galaxies merge, and the black holes merge. And of course, as I told you, there are uncertainties associated with each and every growth mode. And then you have merger-triggered accretion. So the merger process sends down a lot of gas to the galactic nucleus of the merged remnant, and then you can trigger an accretion episode. So the questions, right, we want to answer with our models is that suppose I look at a black hole like the one in the center of the Milky Way, 10 to the 6 solar masses at redshift 0, and I look at one at the center of M87, which is a few billion solar masses. So what fraction of this guy and this guy, they're both at redshift 0, what proportion can the models tell you of this final mass were assembled by each of these processes? I mean, that's the kind of insight we want from these models, right? And of course, we also want this insight to flow through cosmic time. So I want to be able to look at redshift 1, redshift 2, and so on and so forth, look at the population of black holes at each of those epochs, and try and understand how they assemble. So basically, I want to be dissecting the mass history, right? That's what so then question is, how well can we model the properties of the population? And I've shown you all the kinds of basic assumptions that we are going to make that are going to be part of our modeling exercise. And ultimately, of course, can we discriminate between models, right? That's the key question. If you can't discriminate between models, what's the point of building so many models? And then I'll talk a little bit about the current limitations and future prospects. So I've told you before already that we did the back of the envelope argument to show that the energetics of accretion, if we can tap that energy, it's a huge source of energy that can alter the environment. And the reason for that is we see that. We see that on very small scales, there are outflows, and there's a molecular disk. We've seen sort of very complex accretion geometries. Of course, telescoping out to scales that we can resolve. So that's ALMA, that's pretty high resolution. small scale. And then on the larger scales, this is X-ray data from the Perseus cluster, where you see these outflows and shells, and you can see these shells that they're sort of layers and layers of shells that tells you something about the episodic nature of the black hole activity, right? So you have the black hole probably likely switches on, feeds gas, then switches off because it's depleted the gas. Then maybe you have a merger, you have something else that delivers gas to the center, it restarts. So, and you are seeing these outflows that are put out by this growing black hole during its various episodic. So that's one interpretation, and we're going to include that in the model. Sort of episodic growth is something that we're going to definitely include in the models. And so this, just to show you again, these are the correlations. So these are what are observed. Yeah.
Is there a simple way of imagining how mergers trigger accretion?
Yeah, from simulations, I'll show you. So there's a simulation, I have a movie that actually shows, that tracks the gas flow. And then you can see that a lot of gas gets funneled whacked right into the center, the galactic nucleus, yeah. So that is largely driven by, actually both from observational data and simulation. So observational data, you see that in a lot of mergers, there's a huge amount of molecular gas. Lots of CO is sitting in the center, makes it to the galactic nucleus of this really mashed up thing that hasn't quite settled down into the final merged galaxy. So you already see a lot of gas that's there in the inner regions. So these are the correlations. And the question is, so remember I showed you these scaling models, yeah.
It's not a necessary requirement, right? You see, Perseus there's a lot of CO filaments, small, and it's not an obvious merger, right?
Oh, no, it's not a mergers right now, but this is the remnant of the mergers. These are signatures of past mergers.
But CO gas right now.
No, not the CEO gas is not past of merger. His question was about a merger triggered accretion for the galactic nucleus, not about Perseus. Yeah. So these shells are actually the result of feedback processes and the outflows that have been driven. And that was in the X-ray that I showed you. Okay, so here are the correlations that we saw. So there's a correlation, and you can write it out in a bunch of different ways between the galaxy bulge mass and black hole mass, galaxy bulge luminosity, stellar velocity dispersion. So these are the various versions of this plot, and what you see there are bars, but by and large there's this correlation. And as we saw today, we can bracket the model, so we can input, we can ensure that we reproduce this correlation if we assume somehow that the mass of the black hole during its growth phase is proportional to sigma to the sum power, where sigma is the velocity dispersion. And I showed you two ways of thinking about it, where you can actually think about energy-driven, momentum-driven outflows, energy-driven outflows. Those are the two easiest ways that we know to couple the energy from the accreting black hole onto the gas, right? So that's what, and I told you that there's a exponent sigma to the fourth, sigma to the 5. So somewhere in between, but that brackets the possibilities. So that is how this correlation is incorporated as a constraint into the modeling. Okay, so this is all you have to do actually. If you assume that the black hole growth over cosmic time scales as sigma to the sum power, then you inevitably get this. Okay? So that's something we figured out. So this goes as the input. So this is not something we are trying to match. The thing we'll try to match is the scatter, because you can put some scatter in early on, and you can follow the evolution of the scatter, and and you can look at the scatter at various mass ranges, low mass range, high mass range scatter, etc. So the slope is an input constraint to the models. So I just wanted to clarify this, because I have to clarify, as I told you, what observational data serve as input constraints. There are priors in the model, and then what are the predictions, okay? So, I like this version. I just wanted to point out that this part of the plot now this is outdated. It's been really filled in, lots of new data from Amy Raines and her group. So these are very low mass dwarf galaxies, very challenging, but it's starting to get filled in right now. And so this gives you a sense of the errors as well. This version, I wanted to show this, because these ellipses are giving you an idea of the error and the scatter in these measurements. It's telling you something about the accuracy of black hole measurements. So if you ask people who are real purists, they'll tell you there are only two black holes that have good estimates. One is Milky Way, the other is NGC 4258. And they might concede that M87 now maybe does, right, after EHT results. But that's about it. I mean, yeah?
So all of the black hole measurements are coming from the sigma measurements, like using X-ray?
Yeah, they are. So all of these, because this is local, this is redshift 0, they are all coming from dynamics. So this is orbit modeling from spectral data of around the central massive object.
And then they use this to get the
Black hole mass. So you do the orbit modeling because you measure the spatially resolved velocity dispersion profile of the stars. You go as close in as you can, which is why it's restricted to low redshift. You can't do this for higher redshift black holes. These are dormant black holes. They are not growing right now, right? Sorry, yeah, we don't know. We don't know. So what we're going to do is we're going to run two sets of models, one in which this correlation, i.e. MBH-Sigma to the 4th or 5th, is part of the very early input in the initial conditions, and we propagate everything forward with our accretion model, so on and so forth, and then see if you land here versus you don't make that assumption and do you land here, right? So remember I was telling you that this could have an explanation, two different explanations. It could be causation, it could just be central limit theorem if mergers are the most dominant way to grow black holes. So it turns out, I'm sort of let the cat out of the bag a little bit, it turns out that mergers are not the key drivers for the entire black hole population. They are key drivers for the most massive black holes during particular epochs, so at late times. I'll show you how we infer that. Yeah, yeah.
if you're able to model the orbit of the stellar population.
No, I'm not modeling those. People are modeling those. Galactic dynamics, yeah.
Is this the same measurement as Milky Way galaxy?
Yeah, similar, very similar, yes. No, but the error on the measurements, you had a closed Keplerian orbit for SO2 in Milky Way. So there it is not, so it's just a snapshot that they're using to do Schwarzschild modeling, right, of the orbits. In the Milky Way, because of the time scales and our proximity, we can actually sit and watch them for 10 years and see the loop close. It's a much tighter constraint on the central mass, on the mass inside enclosed. So, okay, so then what is it that we want to predict? Okay, so I told you the input is going to be n sigma. So what I want to predict, right, as I told you, I want to predict the scatter. We want to predict the scatter. I've taken the slope as an input. I want to predict the scatter, right? Then I want to predict the abundance and the luminosity of high and low redshift quasars. So my model has to predict. I can slice, as I told you, it's a very rich model. I can slice it, and then I need to be able to match what is seen. Only then I can make predictions, right, for future unobserved populations. So the goal of this, of course, is to open up discovery space to see where are there undetected black holes. We know there are a lot. There's a population that is obscured, highly obscured. There's a population that's very distant, and the population that is very low luminosity. So all of those three classes we've not yet discovered. The question is, are there clever ways to uncover that population to get a full census of how much mass in the universe is actually locked up in black holes? So then we know that the X-ray background is a cumulative radiation from all these black hole populations over redshift. That is exquisitely measured. So it's measured, the error bars are low, and these are current models that tell you that you need a population of growing AGN, some obscured AGN, to give you this observed spectrum. So we've got to match this. Okay, so it's a pretty tall order, but we'll see that we can actually make quite a bit of headway. So what are the things that inform our models? As I mentioned, so there's multi-wavelength data for active and quiescent black holes. And then there's some very interesting observations that we would like to match as well. So we are slowly uncovering a population of very high redshift quasars, extremely luminous population. So once again, I want to stress here that if you found one freak object, if we found only one quasar at redshift 7 that is powered so luminous because we see it, and if it's Eddington limited, we get a mass estimate of say 10 to the 9 solar masses already in place at redshift 7. If it was one stray object, it's fine. Cold dark matter can accommodate few freaky objects. It's a population. We're finding more and more. We found a lot between 6.5 and above. We now have more than a dozen quasars at redshift 6 and beyond. So it's a tail end of a population, but it's the tip of the iceberg in terms of the brightest ones. So clearly there could be a lot of low luminous stuff that's hanging out there we don't know about. So this is an important constraint. So whatever mass model mass accumulation history that I build for black holes, I need to be able to reproduce these few rare objects as well as part of my census, right? So, and so this is and as we saw yesterday, there were two very nice talks by Bani and Gulab where they're looking at detailed modeling of individual sources, right? That is beautiful work, but you don't have that kind of data. You will never have that kind of data for all black holes in the universe, right? And so the idea is that you've got to do this kind of population modeling with sort of averages and bracketing out the possibilities. So the other kind of data we have, this is from SDSS. This is broadline quasars from a redshift of 1 to 4.5. And what you see here are the derived black hole mass function, the mass function of black holes derived from the luminosity function, right? Making assumptions about the Eddington ratio and how, whether they are Eddington limited or not and so on. So this is very nice work, but this is something we have to match. Okay, so we have to match. So when I predict quasar luminosity functions at redshifts, not only do I have to match the luminosity functions, but for the brightest guys, because remember these guys are very bright, this is a very bright end. For the bright end, we have estimates of black hole masses. So I have to reproduce that mass function as well. Okay, so it's a key input. Then there are some other interesting things, some interesting observations, like freak things that require explanation. So one of them is that when you cross-correlate the cosmic infrared background with the cosmic X-ray background, you actually find an excess on large scales, okay? And the objects, and they look like you could have, it looks like you could have an early massive black hole population. There was a prediction that maybe that can explain, this is the excess we are trying to explain, okay, this excess. And there have been claims that maybe the red model is the one, so the black dots are the data. And the red model is the one that says maybe there's an early undetected black hole population that's responsible for this. So, it would be nice if my models can actually explain this without ab initio, because I can produce bolometric luminosity functions, and then I can use a bolometric correction factor for every waveband and get them for every waveband. I can, just as I can compute the cosmic X-ray background, I should be able to compute the cosmic infrared background. So that's one thing that would be nice to do. So there's a new set of things, so this I'm particularly pleased about because, so we've been talking about how at high redshifts you always detect accreting black holes, right? You only see them as quasars or AGN or what have you. The question is, and I've just finished telling you that we think maybe black holes have episodic accretion. So, you have a saltpeter time, they're on, they grow, and then they shut off. And we know from feedback stuff, we know how you could shut them off, right? We saw that as well in that sigma to the fourth argument. So the question is there a large population of dormant black holes right now that are in between active stages? How many do you have? So I think about 20 years ago, at a time when we didn't have much data, we just had the Magorian relation. And I had written a very speculative paper saying that, well, if we are to couple black holes to large scales and their environments, the easiest way to do it would be with their outflows. So if this quasar is going to drive out an outflow, then I just put in some numbers and I noticed that you could sweep up a lot of gas into a shell. So this quasar could, when it's on, it could sweep up a huge amount of gas in a shell. And then this shell of gas, which has about 10 to the 13 solar masses, it can be as massive as that will go gravitationally unstable. And then it would fragment. It could form dwarf galaxies. It could do other things. But because there's so much gas there, it will show up in the Sunyaev-Zeldovich effect. That was the prediction. It will show up as a decrement. And it will show up as a decrement that is away from the actual quasar. So this was a crazy sort of speculative prediction, and it turns out last year they detected the first such outflow in Sunyaev-Zeldovich. And you see it is offset. It's really uncanny that the geometry looks like my cartoon from 20 years ago. So, and they've started to find more and more of them. So we are now going to be unveiling a population of black holes that's actually dormant. They could be quite massive because if they've swept up enough mass, they have to be massive enough because all these models for where you're getting the energy is powered by accretion, right? We are tapping some percentage of the accretion luminosity to drive all these outflows. The accretion luminosity is proportional to black hole mass typically. So you probably had a very bright quasar which shut off, and it has pushed all this mass. And so we're discovering this sort of population. We've just, this particular source that was detected last year is actually modest redshift, is like 1.5 or so. But there's a very strong dependence on redshift with the decrement. And as you all know, the Sunyaev-Zeldovich decrement doesn't get diminished. There isn't the surface brightness dimming that you have with optical light with Sunyaev-Zeldovich. So you are just as likely to find a decrement at redshift 1 as at 10. So, and this decrement in terms of the amplitude of this decrement, it's a strong scaling with redshift. So you should start uncovering. So one new way to start uncovering dormant black holes, once you have a population, right now we have 2 sources. So they're not, my models, it doesn't, I can't make predictions yet. But once I have the surveys find this population, uncover a little more about this population, then, this is an additional, yeah. Just around, so this is just doing surveys around known quasars. So known quasars that are not optically bright. So that may be infrared bright. And also these regions are high density regions. These are protocluster regions. So also what you could do is you do a survey around. So typically people would point at the protocluster region, right? So they use a density map, they look at the overdensity, and that's where they do the pointed SZ observation. So this is basically do a sort of a survey right around where you would normally focus for the SZ. Okay. Yeah, so, sure. So the interesting thing is that, the reason you get this enhancement is because you have both the thermal and the kinematic piece that contribute. So because you have the outflow that's flowing out with some velocity. So this is why this is such a standout signal. The signal gets much larger. The delta T over T has a contribution both from the kinematic piece and the thermal piece. No, the thermal is contributed, everything is contributed by the accretion luminosity coupling and pushing the gas in the vicinity. No, it's not like there's a potential well that has an equipartition, some thermal gas, no. So that's why it was a very peculiar kind of, yeah.
Yes, you said there are 2 effects.
Yeah. Right, both the kinematic and, yeah. And so, the reason you couldn't find it till now is you needed the frequency range where you could detect it and you needed ALMA, yeah.
Out, it sort of creates a depression in the density also, right? So
right,
is that also accounted for does it have an effect on the Y parameter directly?
No, that's
or
I
is
said,
this
the
only
detection,
the temperature?
no, but the detection is the Y parameter, the decrement is detected away from the quasar.
Oh, okay, do it.
So that's why this is the discovery, that little contour there, yeah. Okay, so obviously the first question, right, the first open question is seeding. What are the seeds for supermassive black holes? And it turns out the reason we need to open our minds to beyond population 3 is because you are detecting this population of very luminous quasars at high redshift that have very, very massive black holes in place when the universe was a fraction of its age. If you start from a seed black hole that is 10 solar masses, you cannot build it up. You require an exquisite amount of fine tuning to build up to get 10 to the 9 solar masses by redshift 7.5, okay? So, and there are people who argue, well, maybe we can find, whatever. But the point is that, as I said, I keep stressing this. If it's one object, you can say, okay, fine tune, this black hole happened to find itself in the best possible conditions, and that's the freak. If it's a population, you need a more natural explanation, right? So that's sort of what people like me have been looking at for a long time. So this is an old diagram from Martin Rees of the various channels with which you can make black holes. So this is the particular channel and a version of this, a slightly different twist on this, which is direct gas cloud collapsing and giving you a black hole, right? And so when Martin did this plot, I mean, he was not suggesting that the outcomes of these in terms of the final masses would be different for any of these channels. I mean, people were not thinking about, the population 3 was plenty, and they were just trying to see if there were other ways of making them. So what we did and this is also quite a while ago now, 2006 and 7, with one of my postdocs, Giuseppe Laudato, we started looking into what are the conditions here that could give you a black hole seed that is 10 to the 4 to 10 to the 6 solar masses. What are the physical conditions in the universe that you would need in order to get such a seed, right? So then we noticed that in the standard cold dark matter model, if you have baryons that are inside fall into a dark matter halo, so this is very early on, right? So this is pre-galactic, so the galaxy hasn't formed. This is as the galaxy is assembling, you have a collapsed dark matter halo that has separated out from the Hubble expansion. You have gas that falls in, and typically you form a rotating pre-galactic disk. Once again, as we saw with the flows onto the black holes, whenever gas has angular momentum, it's going to settle into a disk, right? So it settles into a pre-galactic disk. And the way to get this disk to actually eventually give you a central compact object is to make the disk gravitationally unstable, but not fragment. So it becomes unstable in a very specific way, so globally unstable. So you have some bars inside bars, some kind of non-axisymmetric instabilities that will just siphon the matter, right, very rapidly. So this is very much like what you see in a bathtub, right? You take the plug out, and you see very rapid flow into. So it's a very similar process. So the key here is that we have to prevent the formation of stars. Because if the disk fragments and forms stars, then you will not accrete mass to the center, right? And then basically what you can do, you see that the conditions that you need to do that are you need metal-free gas so that you don't cool enough to fragment and form stars, right? And to do that, we need to do this in the early universe anyway, where it's dominated by atomic hydrogen. But you want atomic hydrogen to be the key coolant. You don't want molecular hydrogen to form. And if it forms, it will form in trace amounts. You want to dissociate it rapidly. And to do that, you need some external Lyman-Werner field. You need photons with energy 11.2 to 13.6 eV that would dissociate any molecular hydrogen. So all the cooling would be kept. The cooling physics is simple. It will have to be kept as atomic cooling. So this means this happens in the universe, in the very early universe. So this all works out well in the sense that, this process, we want this to happen very early on the universe, in the universe to form these seeds. And so what is very nice is within the framework of lambda CDM, we are actually able to provide for the first time an initial mass function for black hole seeds. Okay, so this was not possible before. There was no model that would give you that. So that was what was really cool about this model. And of course, as it turns out, you can check whether these conditions are sensible, are they available in cosmological simulations, and you find that they are. Okay? So these are a synopsis of the seed formation. So at the moment, this is our current understanding. So there are broadly two categories of initial black hole seeds. The light seeds are your usual population 3 seeds, perhaps with masses between 10s to 100 solar masses. Remember, there's a lot of uncertainty about the IMF of these stars. Initially, till about 5 years ago, we used to believe that you make one massive star. There's the first star. It turns out that that was a limit of our resolution of our simulations. As simulations got better, you find out that you make a first cluster of stars. You don't make a single star, right? You weren't able to resolve the fragmentation before. Now you see that you make a first cluster, which means what you thought was the mass, total mass of one star, which was several hundred solar masses, is now distributed amongst 10 or 12 or 20 of them. So the masses of these population 3 stars has gone down, which means the masses of the remnants they leave behind is also going to go down, right? So they are roughly in this range. So then we believe that nuclear star clusters, right? So you form these star clusters. Instead of a first star, you form star clusters. So you could have a nuclear, gas-rich nuclear cluster, star cluster, where the black holes from these individual stars then merges, and maybe you can get something that 1,000 solar masses. This is just looking at possible theoretical ways, right? And then there is this direct collapse black hole that I just showed you, where, where I just mentioned, where you have this pre-galactic disk, doesn't fragment, and then you find that you can make seeds that are 10 to the 4th, 10 to the 6th. Yeah.
Possibility of this 100 solar mass type of 3 stars are ruled out now?
Pardon?
Possibility of this 100 solar mass type of 3 stars?
No, 100 may still be okay, but thousands definitely ruled out. 500 is ruled out. I think I have a slide that shows the latest simulation with Hirano and others, a Japanese group. They are working actively on it. And every time they do a better simulation, the mass range keeps going down. Okay, yeah. No, they are not similar. No, I mean, well, I mean, gas and gas cooling and dynamics of gas does everything in the universe, right? So, but here you are forming these objects that have a short evolutionary lifetime. They put out photons because they're stars. They put out photons, and then they eventually give you little remnant black holes. Yeah, the initial formation is efficient cooling, so this is the opposite. This is inefficient cooling, so they are not the same. Oh, no, but that's the key. That's the key. And that's the key, and the key issue is that, fragmentation is permitted, cooling and fragmentation occurs here, cooling and fragmentation are suppressed here, and so this is a much rarer channel, this is a more ubiquitous channel. So this requires a lot of special conditions, as we just saw, right? So you have to have metal-free gas, you have to prevent molecular hydrogen. So basically what that tells you is that the most likely spatial scenario is that you have a halo here, dark matter halo, that is formed population 3 stars, and it's producing radiation, it's giving out photons. So you have these population 3 stars that have formed already, and then in a satellite halo for this, because we want the irradiation from the Lyman-Werner band, you will form the DCBH. So these, we believe, are the sites. The potential sites are satellites. Why is this important? Because you can actually calculate correlation functions, etc. I mean, there's a rich amount of machinery and data that we could get to test that scenario, right? So because we need this external field, we need an external ionizing field to ensure that we can dissociate molecular hydrogen. No, I'm telling you how to make massive seeds. That's for the first star. No, that's not a quasi-star. It's for the first stars, population 3. So then, basically, you need to make these first black holes in pre-galactic halos. So before you form stars, like huge populations of stars, and you start assembling the galaxy and the. So you need to do this between redshifts of 20 and 30. And so here are the various light seeds. This is just giving you a synopsis of what I showed you as a cartoon, and to give you the kinds of mechanisms, right? So, pertinent to your question, in the direct collapse case, we think that you form something that is sort of a quasi-stellar object at late times, and that's how you end up collapsing and forming. We have not been able. This is an open question. There are some interesting open problems here. We cannot see this stage yet in the simulations. I'll show you how far down we can get at the moment. So then, of course, I put in primordial black holes, but there are really no constraints. So here is the initial mass function of the population of first stars. These are not black holes. The black holes are going to have a lot fewer masses, solar masses, right? So these are from bunches of simulations by Hirano and collaborators. And so what you find is that the IMF looks something like this. The blue, there's a bunch of different runs, slight differences in these runs. And as I mentioned, right, so there's a small tail, but there is a pretty sharp cutoff. So you really don't make stars that are 1,000 solar masses. It was believed earlier on that you could make these very massive stars. You don't. So you make this kind of population, okay? And then you might say, okay, why do you need these massive seeds, Priya? Why can't you just push the little seeds, make them super Eddington growth, whatever? Why can't you make that happen? So there's another problem. The problem is that when you now track this cluster of first stars that forms and their remnants, right, as sync particles. So these black dots are the black hole remnants from that first population that formed. So what you find is that these, you can track what's going on with these remnants. They are no longer in gas-rich bits of the halo where they can grow. They get sputtered and scattered out because a lot of mergers, they kick each other, 3-body interactions. And so if you look at these simulations, so these are simulations by a whole bunch of people, Mike Norman, all of these are adaptive mesh refinement simulations where they have a lot of resolution in high density areas so they can resolve and understand what's going on. So these are temperature and density slices in these simulations where self-consistently, cosmological simulation, you form the first stars, they'll bake the remnants, those zinc particles are these little circles here, and then you track to see what's going on over time. And so what you see is that very few of these guys are in the higher density regions. They get scattered out of halos, of dense halos. And you find that by redshift 8, if you have a halo, you zoom in on a halo that's 2 times 10 to the 8 solar masses, there are 25 little black holes, and they have together put on 3 solar masses. That's the growth rate. It's piddly. I mean, this is not going to give us a 10 to the 9 solar mass supermassive black hole by redshift 7. So, they're in the wrong place. So you need another channel to make more efficient growth to produce the, so then there are stellar dynamical processes within the nuclear star clusters. So I'm just showing you a little bit more about, there's some very nice work that was done by Marta Voluntary and her collaborators, where basically you form the nuclear star cluster, and then as I showed you in that cartoon, basically you can actually calculate how the stars will merge into either a very massive star that will collapse into a black hole. That is about 1,000 solar masses. So you could have one of two outcomes. You could have individual black holes, remnants merging, or you could have the stars merging, making a big star, and then collapsing. Okay? So then we did another interesting, we noticed that there was something else that you could do to amplify early growth. So I tried very hard to recover population 3 seeds, right, to see if I could get them to work. So one cute calculation that I did with Tal Alexander a few years ago was that basically if you have a gas-rich nuclear star cluster, so this is the gas that you're seeing in blue, and these are the stars in the nuclear star cluster, and then you have a black hole that does not define the center of the potential anymore. It's not in the center, but it's random walking. And so then it gets wind-fed. So then what you can do is you can argue that if you can suppress the formation of an accretion disk around it, then it's the accretion disk that limits it's the Eddington limit, and it's limited by the radiation, the back reaction of the radiation from the accretion flow can disrupt, all of that feedback and that complex stuff. If we can say that you suppress the formation of an accretion disk, then you can accrete, it's like wind-fed accretion, Bondi-Hoyle accretion, so you can accrete a lot of mass very, very quickly. And the way this will proceed is that this will bounce around, it'll gain a lot of mass, and eventually it'll become so heavy, it'll become much more heavy than the stars, and it'll sink to the center. And it would have depleted all the gas that is there. And we found that this process can grow a black hole that starts out at, say, 10 solar masses, 20 solar masses, by 3 to 4 orders of magnitude, depending on the parameters that are available, amount of gas that's available, and so on and so forth. Yeah? Pardon? No, but the gas density is required very, very high. So maybe if globular clusters at early times had that, but it's unclear that you could have that kind of gas density. But I think you have nuclear star clusters that form very early on in the universe. So that would be the appropriate environment. Yeah. Oh yeah, everything is timing. You can do it 10 to the 6, 10 to the 7 years, very rapidly. Yeah, that's why it's viable. So a little more, I won't spend too much time on this. You guys can look at the slides later, but this is a little more showing you how this direct collapse works and showing you a status of the simulations, right? So this was from a few years ago, and I'll show you the latest update now. So from 2014 and 15, we could actually resolve the formation of this pre-galactic disk, right? So we could actually resolve that, and this is the disk profile. So sigma surface density profile of 1 over r. So you see this inner region has actually a disky geometry. Notice this is 0.01 parsec. So it's an AMR simulation where we can really get down to very small scales. But at this point, 3 years ago, you could not see the matter, this getting unstable, globally unstable. You couldn't see the flows. You couldn't see the rest of the process that we want, but we could definitely see that you assemble a very massive pre-galactic disk that can go and will go unstable. This thing is Q unstable already. Okay. So then, of course, what happens next, we don't know. There are speculations, there are calculations, that maybe what you have is that you make one little black hole from siphoning, you make a little central object, and then you have something that looks like a red giant star, huge convective envelope, radiation supported one, and then that feeds in, and then you get a final mass of 10 to the 4, 10 to the 6. So, if anyone wants to think about places where you could do some new work, this is an area where there's a lot of new work that could be done. And it can be done, combining sort of analytic plus, stellar models. So I think we have the infrastructure already. It would be very interesting to see if you could modify those stellar models for this case. And there have been a few papers, there's been a whole, it's not a crowded problem yet. So it would be a good time if people are looking for something to do. So now let me show you a little bit more about where the simulations are moving on. And so we are able to resolve these pre-galactic disks, and you start to see the next stage, which was those bars. So this, yeah. No, but that's the thing, you have to prevent them from going supernova, right? Or maybe, they will go hypernova, super duper nova, not your classical supernova, yeah. Yeah, but they're extremely short-lived. So the detection of that particular object, we looked into it, it's too short-lived to actually find it. And remember, these are rare to start with anyway. So what you find is that now, with the simulations, you're starting to resolve these. Remember I told you that, ideally, in those papers we wrote in 2005, 6, you need ideally bars within bars, blah, 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 to siphon matter in. So you start seeing them, actually. So now we have simulations that are starting to show us that this DCBH picture is quite viable from the simulation point of view, right? So the question, therefore, is what are the other downstream predictions? Suppose I start with a massive population of black holes, seed black holes. Downstream, can I discriminate that from population 3 seeds, right? So that, because as I told you early on in the universe, to directly see that process happening, it's rare and it's short-lived, which is what we want, right? So capturing it directly with observational data is going to be challenging at redshifts of 20 or 15 or whatever it is. But, so this is just a synopsis that shows you the various ways in which we believe seed black holes can be made. So these are the 3 kind of most popular channels, and we can cover pretty much all the phenomenology that's observed with these 3, okay? And the end states, as I said, the massive seeds, all you need to remember are these, there are 2 channels, light seeds, massive seeds. Massive seeds are 10 to the 4, 10 to the 6 solar masses already when they form redshift 15, redshift 12. And these guys can be anywhere between 10 to few hundred solar masses. And once again, they also form by redshifts of 15 and 20, okay? So now there's been enormous progress. So just this past year, there were 2 simulations, 2 sets of simulations. I guess 2 years ago, they were published in 2018, that you can see that people have started to follow the DCBH. So then the question, and we've come to this before, which is, okay, this is great, but if you are making those seeds, then that's telling you that you have a class of intermediate mass black holes. Where are they, right? We haven't found them. So once again, I wanted to show you that this is one of my favorite candidates, and this is a believable one. It's off center. I showed this to you earlier. And so maybe the way we've been searching for them, we've been looking for them in the centers of low mass galaxies. Maybe that's not the way forward, and maybe they are all wandering, so that's why they've been hard to detect. And in this particular case, we detected this guy because it actually gave you an X-ray outburst, like a TDE type outburst, right? So maybe TDEs are going to be the way, tidal disruption events are going to be the way, especially if they're sitting in very gas-poor parts of the halo, they're not going to be growing all that much, they're not going to be that luminous to be picked up at the moment, right? But I think that is sort of the open observational question. We want to fill in the observational data there. Okay, so then if you see, I don't need to belabor more that you need massive seeds. There are other issues. So when we try to match, when we build these models without the massive seeds, initial seeds, and we try to explain, remember that black hole mass function from SDSS, broadline quasars, actually we cannot match them. And it's not surprising because remember that is the massive end, the brightest quasars, most massive black holes at epochs redshift 1 to 4.5. So you really need, there's a lot of observational data that requires you to have more than one way to make black holes, or at least start out with massive seeds in the get-go, okay? So now let me talk, so now I'm going to break the problem into early growth and later time growth for black holes, because there's actually, the conditions in the universe fundamentally shift. In the early universe, you're very, very gas rich, and so black hole growth can progress much more efficiently than it can at later times, okay? So I'll focus now. So now we are building these population models, but let's look at what's happening at early times. So what we did is we did first, to understand what's going on, to look at whether this massive seed, whether you start from 100 solar masses or 10 to the 4 solar masses, does it have an impact on early growth? Okay, do you have more efficient growth if you start with an initial more massive seed in a condition that is, in conditions that are typical in the early universe? So we did a bunch of idealized simulations. So basically you have a seed with some initial mass, and we did that for both low mass seeds, the light seeds, and the heavy seeds. And you have an atomic cooling halo where this, for example, a typical DCBH would have formed at that epoch, virial temperature about 10 to the 4 Kelvin, and then you solve, it's a code that Fabio Pacucci, one of my former postdocs, developed during his PhD thesis, which we then purposed for this particular problem. And so you have spherical symmetry, solve Euler's equation, solve radiation transfer, and then you have the cooling and opacity. So you're looking at the self-consistent growth of this black hole and any stars that might also form. Okay, so this is, you're started off at early times, and then you see what kind of spectrum this growing black hole would have. Okay, and the composition would be usual sort of, you try to see these components, a multicolor black body, power law, and a reflection component. And as we saw yesterday from the detailed modeling that is done for AGNs, we know that you probably have these 3 components, minimally at least, right? And then you post-process using some canned program like Cloudy, and you can put out a spectrum. You can generate a multi-wavelength spectrum. So that's what we did. And to do that, to set off the initial conditions for those simulations, you need to make a decision. How is the seed going to grow? Is it going to grow just Eddington limited? Is it going to grow differently, right? So it turns out in the early universe, you have a lot of obscured sources. So you have sources because of dust, gas and dust in the early universe. You could have obscured sources, and therefore we should at the very least, once again, bracket the possibilities, and the 2 bracketed possibilities are Eddington limited standard thin disk stuff that I've talked about. And so where the luminosity, the output accretion luminosity is proportional to the mass inflow rate, this is the accretion rate. And the other case is when the luminosity is proportional. So this is the case, is one of the cases that Barney talked about yesterday in his diagram of all possible models, accretion models. This is the slim disk model, okay? And the reason is that the slim disk model is the most pertinent one for high redshift universe, right? So here the accretion luminosity is proportional to the logarithm of the mass accretion rate, okay? So which means that you can have super Eddington mass assembly with very low luminosity, okay? So that's the difference between these 2 models. So in this mode, you assemble mass. The mass growth of the black hole is incommensurate with the luminosity, unlike the case for Eddington, okay? You can grow the black hole much more rapidly, and the luminosity will not tell you that, right? So it's the geometry. So these are the 2 different sort of bracketed the possibilities. And so then you can calculate, with the various spectral components. And then you find, when you run those models, I'll go through this very quickly because the thing you need to get out is that there are actually the growth of those early seeds occurs in these 2 modes, right, that we just started off as initial conditions. And what you find is the feedback limited growth, that is the Eddington growth, okay? So the Eddington growth is actually, mass growth is very inefficient, relatively speaking. You have lots of outflows. Only 15% of the gas actually even gets accreted. So it dribbles. The black hole is dribbling a lot in this case. When you start out with heavier seeds, you find that you are in a different growth mode. So you are set off in a different growth mode, right? And that is because you will form the heavier seed in a more dense gas environment. That's how you produce these direct collapse black hole seeds, right? They are the rarer, densest halos. So they are much more gas rich. There you have super Eddington growth, and your outflows are not so important, and you have very low radiative efficiency, and 80% of the gas is accreted. So you grow much more rapidly. So if you start out with your initial condition being a massive seed, given how that massive seed needs to form in the universe, it will also grow very rapidly. You get a head start. Okay? So there are lots of details and many papers, very interesting papers if you want to look at them, work that we've done over. And so once again, we looked at this and we see that the optimal growth conditions you have, the optimal growth is really for black hole seed masses between 10 to the 4th. This is the DCBH range. And this is the population 3. So you find that the reason is that the key physical quantity that determines the growth is actually the gas number density. And just via how the massive seeds form, they form in more dense gas-rich environments. Okay, so they have amplified growth. Okay, that's very interesting. So now we know that very early on, these massive seeds can grow and have a head start, but they're very rare. This is all looking very good to explain those bright quasars at high redshift. So then the question is, can you test this model? It turns out there's something very cool at high redshift, right? So if you look at the formation of a direct collapse black hole, so I told you this is the rough kind of scenario we believe, right? So there's a dark matter halo that forms the first population of stars, and then a satellite halo will be where the DCBH forms, okay? So obviously, if this guy is a satellite, it's going to merge very rapidly in CDM early on in the universe. And so let's assume that this galaxy that formed the first population, let's assume, say, 2 different parameters, slightly low metallicity, slightly higher metallicity. This DCBH is going to merge, right? Because it's a satellite. That's the preferred spatial configuration conducive to the formation of the DCBH. So then you get this very interesting object which has a small stellar population, and it has the DCBH. And it turns out that during a small window in redshift, from redshift 12 to redshift 9 or so, this object exists. And the peculiar properties of this object are that it's completely inverse of the galaxies we see on M-Sigma today. So remember, in M-Sigma, we see that the mass of the black hole is 1,000th the mass of the stars. Here, the black hole mass dominates the galaxy. The mass locked up in this black hole is much higher than the mass in the stellar population. And the entire spectrum will be dominated by accretion onto the supermassive black hole. But there'll be a stellar component. So you'll see some stellar lines and so on and so forth, right? But this is the complete converse of what we have. And then these objects, so direct collapse black holes, will then have to eventually grow over cosmic time and land on M-Sigma, invert everything and land on M-Sigma, where the black hole now is not as massive compared to the stars. So the stellar assembly, it's telling you something about how stellar assembly will proceed preferentially in galaxies that are seeded with a direct collapse black hole. It's a fundamentally different track, evolutionary track, compared to population 3 cases. So, where you form a population 3, yeah, that guy will also merge. And now the mass of the black hole in this merged object is going to be, it's going to be small compared to the full stellar mass content. So the spectrum is going to be fundamentally different. And so this is just another way of showing it, a nicer way to show this cartoon plus that. So you have this pristine halo, Lyman-1 of photons, you form the DCBH. So we call this object an obese black hole galaxy, where the black hole is overmassive compared to the stars. Kind of slightly unimaginative name, but whatever. And then you have this galaxy with a POP3 remnant. So now the goal is, so these objects will exist. Why do I say redshift 9 to 12? Because after 9, you start forming stars, right? This guy will merge with some other galaxy, and you keep adding to the stellar population while the growth is also, for the black hole, is also moving along. But you rapidly add stars because you merge with other galaxies after that, right? So you move away from being dominated by the black hole mass. Okay, so then what we want to do is we want to calculate spectrally what these two cases are going to look like. So that's what we did. And you can actually, so this is actually a movie that I can show you later. I don't have it's just a static slide, because what I wanted to show you is those kinds of objects have spectra that are quite fundamentally different, because they, most of the energy output, this is the X-rays, most of the energy output does not come out in the X-rays, actually comes out, it's re-radiated in the infrared. Okay, because remember, these are also dusty, whatever I told you, the gas density is very high. So, so we calculate this full self-consistent multi-wavelength. So these are what the spectra look like. And these are different time slices as this thing is growing and evolving. This is mega years. And so you see that there's energy in the X-rays that gets redistributed into the infrared. And so this is the JWST band, right? So the gray band here. So notice that you can actually see quite a lot of these. They are detectable. The question is the sensitivity. We'll see that in a minute. And so you can see that these objects at one particular stage might be in the Chandra deep field. Okay, the X-ray fluxes might reach there, right, somewhat. So this is the flux limit of the Chandra deep field, the 4 megasecond observation. So this is interesting, because if at some stage they are X-ray bright enough to be seen there, then we can select candidates using other features that we see in the spectra here. We can do color cuts and select potential objects, right? So, yeah. 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 Ultra high, yeah. It's reprocessed, absolutely. Yeah. So, and very clear cut. That's a I'll show you the spectrum in the JWST band from 1 to 30 microns. You can see it very clearly there. Yeah. So what you see, so you can do, I mean, I told you these models are very rich, right? I can do all kinds of parameter slices. So I can start with a POP3 seed with a stellar component, have a standard disk and the high metallicity. I can start with the DCBH seed stellar component and the standard disk. I can also look at the slim disk. I can look at, so basically you can see that there's a lot of flux in the infrared. So all you really need to note from these plots, right? Forget they're all detailed, whatever, you can look at them later, is that a lot of energy from the X-ray is reprocessed and pushed into the infrared. And especially for the DCBH seed, right? And then you can do it for the slim disk case, and you still see once again that there's a lot of, and this is the DCBH there. So here, that's what I told you. Here you can see that when we run these simulations, you see that there are stages where you could have been a source in the Chandra deep field. So you could have a selection from there. Okay, so now these are okay, so now we are going to focus on the spectrum for in the 1 to 30 micron range, which is the JWST band, okay, in the infrared. And so these black things are the sensitivity limits for JW, and notice these things are booming well above the sensitivity, right? And pointing, just getting back to what Prajwal pointed out, so the spectrum will have really sharp distinguishing features, a very peculiar kind of spectrum, a very sharp change in slope from 1 to 3 microns. Okay. So this is just the hydrogen and helium recombination lines that I've plotted at the moment. I've not done all the lines. Okay, it looks very crowded when you do it, but we can do it. We can do that. But, so what you see, and these are the two different metallicities for this. Remember that galaxy that merged with this is for the OBG. So this is slightly lower metal, 0 metallicity, and this is minus 10 to the minus 3 solar. So you still find that you can see these, you can detect them. Because you have this sharp change in slope of the spectrum between 1 and 3 microns, you can actually have some new selection criteria that allow you to select these sources. And to give you some perspective of other confounding things that would have spectra that look like this, so these are dusty old galaxies. These are young star-forming galaxies and dusty galaxies that also radiate a lot in the 1 to 30 micron waveband. So that is this blue and that this gray. Notice the spectral shapes are fundamentally different from my OBG. So you can really discriminate between the OBG and these other classical sources that can contaminate. And so these two different lines, so these are for the massive, so for the slim disk and the standard disk for the two metallicity. So this is sort of the full parameter space. So this is obviously massive initial seeds, right? Those are the OBGs. Yeah. No, no, it's not. This is not redshift. This is metallicity. These are all redshift 9. Yeah, yeah. Yeah, these objects will not exist at 0, right? By the time you get to 0, you're on M sigma. Yeah. So the metallicity has a big effect because there's a stellar component and the evolution of the stellar component, right, and the formation of new stars. So we permit all of that. So we are evolving the stellar component as well over that interval. When I'm evolving the accretion, when I showed you so many mega years and so on, we're evolving the stellar component as well. So the metallicity has a really big effect on the stellar component, and I've added the spectra because this is the composite spectrum of that object. And obviously, that's what we're going to see. Pardon? That's right, yeah. Pardon? It depends on the gas mass, of course, as well, yeah. Yeah, so because remember I told you we did those idealized simulations, right? So these are the outputs from those idealized simulations where I started out with the seed, the gas density, and then the only thing that's different is that now I've added in the evolution of the stellar component as well. So, yeah.
I understand, the DCBH scenario is going back to the slides. You try to avoid, metallicity, keeping it low metal so that
when the DCBH forms, but after that it doesn't matter.
Yes, right. So my question is, even for the formation of DCBH, you'd still have to deal with H2.
That's what I said, molecular cooling has to be suppressed.
Suppress, so how do you do that?
Lyman-Werner photons.
That's what you use.
Yeah, that's what, so you need external ionizing source to dissociate H2. So you then have only atomic cooling. That's what you need to do for the stage before you form the DCBH. Once you form the DCBH, then you don't need that. I mean, then you have the stellar populations, yeah.
So the question is, where do you get that?
Did you doze off? Okay, because you make, so this is the scenario, right? So you have a halo that forms the first population of stars, and the DCBH forms in a satellite galaxy, satellite halo to that one, so that it will have irradiated Lyman-Werner flux. Yeah, that's what's good. Yeah.
For DCBH, the diameter has no mass, very massive, about 10 solar masses. So,
Moving 10 to the 8 solar masses, 10 to the 9 solar. They are rare halos. They are high 5 sigma peaks. Yeah.
you need real temperature of your can.
Yeah.
Those are the real temperatures.
Yeah, but they will be for rarer things, right? So the only thing you can have that virial temperature for a higher mass, which means those objects will just be rarer.
Yeah.
Right.
For that massive halo, which is satellite,
Yeah. So that's right. So that's why they are rare, right? So that's why they are rare. This configuration is quite rare. So the mass difference between these two will just be an order of magnitude at most.
and as I remember it correctly, earlier we were saying, so you need some critical flux.
No, there you don't need a critical value. That's a unnecessary. That's a dispute that was going on. There is no critical value of JW that you need, the flux that you need of the Lyman-Werner band, J crit. You really don't need J crit because, I mean, I have isolated. Look, in the universe, this is not the only thing that's happening, right? I mean, there is going to be a lot more Lyman-Werner flux that's coming from other guys that have all formed stars all over. So there's a background flux. There's a background field, ionizing field that is there. But this would be the optimal if you can rain down from really close up, right? The reason we like this scenario is because we can calculate the statistics of this scenario. Yeah. There is no critical value. No, it's resolved. Yeah. No. There was like a waste of time, many papers where people thought there was a critical value, that you needed a minimal value. You don't need a global minimum value. It's a very local phenomenon. So you really cannot talk about a global critical value. Yeah. Yeah, we see that. So there are papers that published with one of my former postdocs, Bhaskar Agarwal. So we went into a simulation, the simulation called Phoebe, which is the first billion-year simulation. And you actually find these. I mean, you find the configurations where, yeah, and the abundance was fine. They're, yeah. Yeah. Yeah, but I've told you already that, come on, yeah. Type 2 quasars don't have so much of the flux coming out in the infrared. Well, we don't even know if there's a type 2 that exists. I mean, look, this nomenclature is irrelevant at redshifts 9 and 10, right? It's not even clear that the orientation model is the key discriminant for various types of quasars, right? Even at lower redshift. But yeah, I don't know. I mean, you can have your primordial black holes or whatever. You can have whatever you want. Give the. No. But stars form in special locations. DCBH will form in a special location. So I don't see if you had primordial black holes that are, okay, I just don't want to go there. It's a complete waste because there's no constraint on that scenario. I don't like it when, I mean, I'm not interested in making models. So if even a portion of this guy's dark matter halo is made of PBHs, then you are creating radiation that will prevent the formation of the first stars to start with. Okay, so let's just stop there. You won't even form the first stars with your PBH story. So here, and then you have to do a very contrived model that, it's not actually dark matter, but it's actually floating, free-floating PBHs that are accreting. You have to fine-tune their accreting so that they don't overproduce. Forget it. I mean, it's just, there's nothing there right now. I mean, if there is some data that will give me some constraint, sure. Then we can play with the model. Yeah, but not for how much in omega you could lock up in that PBH. They're very loose. They're not enough to tie into these models, right? I mean, feel free to work on them. I'm not interested. That's all. Okay, it's a personal prejudice, and I'm admitting to it. So, but if you look at the population 3 case, you find that they should be undetectable. The flux is below JWST sensitivity. So we went out. We are out on a limb, and we have said now that if JWST detects any quasars, any accreting black holes at redshifts 9-ish, 8 to 9, because it's all a little loose, there's no tight 9 to 12 or whatever, right? It's a little bit of leeway there. So any quasar, any luminous quasar that JW detects at extremely high redshift, we are arguing has to have had a direct collapse black hole seed. And because a population 3 seed just would not have enough. Yeah. Yeah, it'll be an OBG, yeah. And that's right, because then that tells you something about the properties of the host galaxy as well. If you find it, then it tells you that it's going to be a low stellar mass population, et cetera, yeah. So that's sort of what we did. So, okay, let me now show you modeling the population. So I think I'm going to go over today. I hope it's okay. Only because I want to reach the end, right? We finished today. I really want to show you the end. And many of you have had great questions about the seeding and the consequences over the last 2 days. And I kept saying, I'll tell you tomorrow. I'll tell you on the third leg. So this is a simulation. Let us see if I can get this to work. No. Okay, so this was what this would have shown you. This is a video from one of my former students, Pedro Capello. So you see these 2 gas-rich spiral galaxies merging. And they have central black holes. And this is a movie, it's available online, where you can see the way he's visualized the growth with flickering. The center flickers when it's actually growing, right? So mass is accreting. And then you will see the final stages to answer the question of gas flows. You'll see in the final stages of the merged remnant, So you see only the gas here. We are visualizing only the gas. There are stars, there's dark matter, there's everything in the simulation. You will see there are gas flows that go right into the galactic nucleus. So you can reactivate and trigger accretion, etc. Oh, you think it might work if I try here? Oh yeah, maybe. No. Okay, so as I told you, the approach that we took to the problem is to try to integrate many things. I'll go through some of these things very quickly because I have mentioned these before in terms of the overall approach. So really what we want to do is to build a model where we start with an initial seed population at high redshift, cosmological initial conditions, seeding, and then we have growth modes. They can grow by Eddington limit, super Eddington, sub-Eddington, you permit everything, and then you follow these black holes as they are assembling and growing over cosmic time. And essentially, they obviously have to land on M-Sigma because we've required that they have to land on M-Sigma, but what we want to see is how much scatter and whether, and along the way, what are the variables? What are the predictions that we can make so we can predict luminosity functions and the evolution of the luminosity function, can predict the X-ray background, we can predict gravitational waves from the mergers, we can predict occupation fraction, what fraction of galaxies today in different mass ranges should harbor a black hole. So these are called, they were called by people like Rachel Somerville, Gunnar Kaufman, who started this as SAMs. And so our version is slightly different, and we call them SEMs. They're semi-empirical models that are much more driven by data, because at the time that these guys developed it, there weren't as many sources of observational data, multi-wavelength data. And this is sort of what I did for my thesis in 2000, where basically integrating black hole growth into the assembly of galaxies, into lambda CDM, okay? So this was right after sort of the M-Sigma stuff. So, okay, so what do we do? I'll quickly skip over this because it's all in papers. You guys can find out how this is done. You start with a merger tree, dark matter merger tree, and then you seed with either a massive seed or a light seed. And then for each time step, you grow the whole with accretion, different models for accretion. And then it's a question of bookkeeping all these various sources at various redshifts. And so this is sort of a schematic. So this is our initial seeding masses, 10 to the 2 to 10 to the 6 solar masses for black hole initial seeds. And so this is the POP3 seeds. This is a more sort of generous DCBH initial mass function. And then we populate, we draw from this. So we do one run with massive initial seeds. We do another run with light seeds. Obviously, in nature, it's going to be a combination of the two, but we are trying to figure out, can we discriminate between them, right? So, okay, so what is new? As I said, one of the key inputs is the observed slope of the M-Sigma relation, okay? And the way this manifests, how does this enter in the modeling? It enters in the modeling when, for example, you have to stop the growth of a black hole, right? So remember, I showed you those two arguments about how to stop the growth of a black hole. How do you get a limiting mass? So, so you have an accretion episode. They have some steady accretion that is continuing on over cosmic time. There's a steady trickle, slow trickle. On top of that, you have these mergers and merger-triggered accretion. So when you trigger a merger-triggered accretion, when do you stop growing the hole? Because it can't keep growing forever, right? So you cap it to mimic the feedback, the radiative feedback from the growth of the black hole that suppresses its growth. And so this is where, remember I told you, you pick an index, whether sigma to the 4th or sigma to the 5. So this is where it goes in the model, right? To show you how the data is being incorporated in the model. So how do these models work? You start with a dark matter halo mass. Then you use data to map between halo mass and stellar mass. That has been done for, of course, we extrapolate some of these relations to high redshift, right? So these are now measured for out to 4 or 5, but we are extrapolating them to higher redshifts. Then we also have data that relates the stellar mass to the sizes of galaxies as a function of redshift. And we use a combination of size, stellar mass, to actually give you an estimate of sigma, because this has been a problematic thing, because in the M-Sigma relation, the sigma is a measurement of the velocity dispersion of the stars. It is not the circular velocity of the dark matter halo that the black hole is sitting in. And these models are driven in lambda CDM by dark matter halos. So in order to get something that is as close to what is measured, sigma, this is what we do. And then we have the black hole, and we follow the growth, okay? So here is just a set of models that we pursue. So you have stochastic accretion. So you use the observed Eddington ratio distribution from X-ray data. You draw from it, okay? And so that is one model. And we include, these are the features in the model, okay? Then we include short timescale variability, this flickering, which you would have seen if I had gotten that movie to work, that there is a lot of short timescale flickering. So there's a lot of anisotropy in the growth. It's not like a steady growth. And so we can model that by using a kernel, time variability kernel, when we convolve to produce the shape of the luminosity functions. And that is sub-mega year variability. And then the two different seeds. And then we have these two models of accretion. I'll show you, we have even more. We have 4 models actually in the end, and we'll zero in on 2 of them. And then the idea is, can we, so these are some details that are, this is how you actually sample the observed Eddington ratio, and and you can look at simulations and see whether the black hole accretion follows star formation, et cetera, et cetera. And you find from the data, Maleni et al. Found that there is a possible linear relation between black hole growth and star formation rate. And we are going to input that as one mode of black hole growth. And that is justified. I'm just showing you that that is justified by what is seen in simulations, and this is from data. This is Maleni et al. Is from data. So basically then we have our current models previous to our work was that basically you have a major merger, you accrete a lot of mass, so your accretion rate is very high, then you stop. And this stopping is how you implement the M-sigma, sigma to the 5 or sigma to the 4. And what we are doing instead is that in addition to the merger trigger, there is a steady growth that is happening all over cosmic time. On top of that, you have the merger, and you have this stochasticity, this variation, small scale variability that we are adding on, okay? So we find that we have to add these elements actually. We did it with a minimal set, and we found that you couldn't reproduce the data. You need all these elements to reproduce what is seen. So these are the, so I want you to focus here. So seeding, we use these 2 different seeding models. So use a burst model where you have it triggered only when a major merger occurs. That's only when you have feeding. And then other than that, it's growing at Eddington rate all along, right? And then it stops once mass exceeds this feedback cap that is put in by M-sigma by hand. So in the steady mode of growth, this steady mode that you have, we put in 2 sort of possibilities. One is this AGN, it's called the AGN main sequence model, where the black hole accretion rate is proportional to star formation rate. Again, this is from empirical data. Then you have a power law model, which is an Eddington ratio distribution that is derived from X-ray luminosity functions for AGN. So we draw from either of those. So you have you start with a population of black holes at high redshift. Do one seeding or the other, then you grow them with these 2 models. And then you have to make an assumption for the mergers, because mergers are a channel by which black holes are going to grow, and which I showed yesterday about the probability, because the dynamics is uncertain. You have to say something about. So then what you find is that for, I won't do the detailed diagnosis, so I just want to show you what all we can do with this. It's very powerful. These models are very powerful because of how many observables we can extract from these models. They're very rich. So the only things I want to show you, so this is a mass assembly history for, so these are Monte Carlo merger trees, right? So you have many candidates. So here are just a couple of accretion histories for 3 very massive seeds, initially massive seeds, 3 light seeds. And so this is the mass assembly as a function of redshift. So you're starting with a light seed, so you're very low mass. And then this is how the growth tracks for 4 of them, okay? Just 4 samples. This is not representative of everything. This is just 4 samples to show, okay? And what you find is that they kind of trickle up. This is with all the accretion modes and everything that I've shown you. And then they eventually, we were trying to produce 10 to the 9 solar masses at redshift 0, right? The M87 hole. So basically you find when you start with a heavier seed, initial seed, notice that the growth is kind of different. The growth histories are very different, okay? Why are they different? Let's draw the M-sigma plot. So what you see in green is the M-sigma slope at redshift 0. okay? But on that, I can plot the tracks because I'm tracing sigma for the galaxy that it's sitting in. I just showed you how we got that. And so notice that for a light seed, when you start off at early times, these are tracks at various times. Remember, at the end of the day, you're going to end up here on M sigma at redshift 0. And the way you reach there is that you are always under massive at early times to the local M sigma, and then you catch up and you form stars. So there's a sequence here of whether the black hole grows first or the stars grow first, right? That is different in each of these. These are just tracks over time.
Okay, so different curves represent different redshifts.
Yeah, different. No, the same black hole at different redshifts. Okay, here. You just have to end up at 10 to the 9. Basically, what I want you to see is that if we can produce M sigma at different redshifts, that would be an important diagnostic, very important diagnostic, because these early massive seeds start out, this is the OBG stage, right? They're above the M sigma today. Then the stars assemble. Black hole doesn't grow very much, the stars assemble. Then immediately this particular black hole has a merger, so it's jumping up here. Yeah, I'm tracking the mass of the black hole over time. That's what this is. These tracks are the mass of the black hole because this axis is still MBH mass. So you start with a heavy seed, you are over massive at early times compared to local M sigma at redshift 0. So that tells you that when you start with a massive seed, you most likely grow the galaxy for a while, okay? So the galaxy catches up because remember the stellar mass is low here for these OBGs. Stellar mass catches up. So how you journey on to the M sigma is determined by seeding. So the seeding is very consequential, and so if we could actually measure and produce these M sigma plots from observations at redshift 1, redshift 2, redshift 3, then we have a lot of discrimination between the models. It's very challenging, of course, right? So this again is probably not going to show because I think I probably made a mistake embedding these. I didn't embed these movies properly in the PDF. I'll try to show you that because it's a nice visual. But let me first show you the results. Okay, so these are the kinds of things you can do. So these are the reproduced M sigma for the various models. So this is the various accretion models and the seeding. So this is just showing you accretion models for massive seeds. So these guys have all had the same seeding, okay? Only the accretion model is different accretion models. And so what you can see, I told you, right, it's a scatter. So can you predict, can the scatter that you observe and you measure in the M sigma, can that tell you anything about either seeding or accretion physics? It turns out that it can't tell you much about seeding, but it can tell you something about accretion physics, okay? But you need really high quality data, right? Then the interesting things that we match, so we match a lot of things, we match things well with these various accretion models. The question is we are trying to see all the observers. So this is the local black hole mass function. This is the M sigma converted into a mass function, okay? That it's just made into a histogram for everything that we have. So that's the black one. And with various accretion models, you can't quite reproduce it. So you can see that some models don't work so well to reproduce this particular observation, right? So we can predict these mass functions. These are not measured yet. None of these are measured. So these are predictions for what the various models. So then you can also predict luminosity functions, right? So these are the predictions for, I have a nicer version of this plot. This is a little cluttered. It's because I'm showing you all the models in this. I'll show you the models that perform best in the next few, okay? But here just showing you that these are all the models, and you can see some of them do very badly at low luminosities, and some do really underproduce the high luminosity end, and so on. So this is all data, real data that you see. And this is what we need to match, and we can actually match them very well. So let me just, these are all other diagnostics that we can do. So these are two models that work somewhat better. There's a cleaner version that'll come up in a couple of slides. So then there's another new diagnostic, which is very, very, yeah.
In these plots, the lower redshift sampling will be different from at higher redshift. Like you preferentially sample the most powerful at higher redshifts.
But we are matching to all the surveys, right? So because we produce a bolometric luminosity with a bolometric with a correction factor. I can tell you that. Yeah, absolutely. Otherwise you can't match, right? Otherwise it doesn't make sense. Yeah. So these are exact comparisons in terms of the flux limits of the surveys and everything. So from our model population, we will extract what can be seen by Chandra, what can be seen in SDSS, et cetera. Yeah, absolutely. So then here, okay, this is a diagnostic that I like very much, which is unusual. We didn't expect this to be so revealing. And this is the local occupation fraction. So this is the fraction of galaxies with stellar mass above 3 × 10⁵ that actually harbor a central supermassive black hole as a function of stellar mass. So this is, basically this is the low end. So this is, dwarf galaxy-ish right here. Challenging to find black holes, but people are starting to find them, right? So the blue boxes are predictions from our models, okay? So this is the light seed, power law, so different accretion models for light seeds. This is massive seeds. And what you see in black are the data from Elena Gallo and Jenny Green and collaborators, Amy Rines and collaborators. And these triangles are Elena Gallo's data from the Virgo cluster galaxy population black hole sources. So X-ray sources, active X-ray sources in cluster galaxies in Virgo cluster. So I'm not going to claim that this is the model that works, but it looks like you can use this data, this particular statistics is giving you power for discrimination between these models. So right now, I think this heavy seeding model, heavy initial seeds with an accretion history where the black hole accretion rate is proportional to the star formation rate. That, remember, was an empirical observation. That appears to work very well at the moment, okay? So then I think there have been questions. I added this slide because people were asking me questions last time about, what can you really learn about the actual merging environments of binary supermassive black holes. And I kept telling you, well, if gas affects the merger, you can actually do a lot. So the electromagnetic counterparts that you could get are, for example, so this is the luminosity. This is from Jorge Quadra's simulations, really beautiful simulations, where basically you have a primary black hole, you have an accretion disk, and you have a secondary that plops onto the accretion disk. The accretion disk is your standard sigma 1/r accretion disk. Nothing peculiar. Then the secondary drops in, it makes its way in, viscously goes in, it opens up a gap, does all of that. And so this is just looking at the emission, the resultant emission from the perturbation set up in the accretion disk. Okay, so you see the emission from the inner disk and the outer disk. So this is the model that shows you as a function of a bolometric luminosity, as a function of time from when the secondary is plopped in, right? And so these are actually measurable in a range of wavelengths. So these are the spectral output from infrared to X-ray. So you should be able, so this is the kind of rich electromagnetic counterpart information, that precursor, postcursor information that you could get. Jorge Quadra. So I did the earliest ones with Phil Armitage. They're too old now. I mean, we did some other ones where we looked at the eccentricity evolution, blah, blah. No, all hydrodynamic, because this is still very much in the hydrodynamic stage. So that is the stage from which we are going to get the richest electromagnetic counterparts, long-lived enough for them to be detectable. And I think that Quadra has done 3D simulations. Hayden and McFadden and Hyman have done 2D. So it depends on whether you believe the 2D versus the 3D. These are very, very nice. I recommend those. Okay, so as I said, the scatter is something we have made very concrete predictions for these models. And then, okay, what are the future predictions, right? So I told you we can match the luminosity functions at lower redshift. So here are the predictions for the luminosity functions of quasars at higher redshift, at 6, 7, 8, 9, 10, 11. And this is just to show you that we compute the bolometric luminosity, so I can actually, with a correction, I can tell you the X-ray luminosity about any band, right? I can do any band. So this is if you have a mission like LINX, which is a proposed mission in the US. It's an X-ray surveyor. So that's the limit. So you should be able, LINX will be able to detect all of this. So once again, the cooler colors are heavy seeds. Orange and yellow are the light seeds, right? So initial seeds. And the two different colors, the orange and yellow, are the two different accretion models. Notice that you cannot separate out seeding and accretion from the luminosity functions, but you can separate out seeding very clearly from these higher redshift luminosity functions. And that basically the change in slope is driven by the abundance of the seeds. So the reason you have a sharper slope here for the light seeds is they are more abundant, much more abundant, compared to the massive seeds, which are less abundant. And then this end is determined obviously by the maximum seed mass, because that sets the luminosity that you can actually produce and what can be detected. Right? So I mean, as you know, the Event Horizon telescope, the reason I had that slide in there is that in some sense, it has led credence to all this idea of accretion and the gas disk, et cetera, right? Remember, it was an untested hypothesis. It seemed very viable, but now we know that that's a very good description of what's happening close to black holes. So once again, for these various models, you can sort of slice and dice the parameter space in a lot of different ways. And this is just to show you that these models are highly predictive. And so there are two papers that we wrote with my student Angelo Riccardi that are published in 17 and 18, where you will see a lot of this parameter space stuff worked out and details of this particular kind of population modeling. And yeah, so as I said, the prospects for discriminating with these kinds of, the dormant black holes at high Z, we want to see what that population is as well, because our models can actually predict that. And then you might say, okay, JWST is not a survey instrument, right? So how are you going to find things that are going to be these OBGs? I just told you that, these OBGs should be there. If JWST finds anything. So it turns out that you can use the dropout technique using X-ray and IR fluxes. So current Chandra data, Herschel and Spitzer data. And you can actually find the dropouts, and we found the selection criteria that work for these sources. So this is from a paper, I think, Metz, Natarajan, and others in 2017. We made concrete predictions for how you would select these sources, because then you would do pointed observations. These are potential DCBH candidates, OBG candidates. So I think, this is, in terms of time scale, I think this is going to be the earliest, assuming everything goes well with JWST, this is going to be the earliest data set that would discriminate models. So the other thing, of course, is the abundance of accreting black holes. So this is, again, just the number of AGN in a deep field that you could have in this potential future survey instrument. So once again, you can see the abundance. These guys are rarer. So these are the massive seeds. They are rarer. These seeds are more ubiquitous. So you should be able to, and this is something that I showed yesterday already, so I'll just flash it very quickly, that once again, for seeding, gravitational wave events are going to be, signatures are very, very powerful. And sort of the high, and yeah, I could, and there's a little bit more that you can do with the massive end of the local black hole mass function and the properties of the most massive, these sort of ultramassive black holes. So that is something that I am most interested in right now. Because we had proposed almost 10 years ago that there has to be an upper limit to black holes. And the question is, in these models, what are those? So those arguments were just from physics, simple physics. Question is, what do these models predict? And the data are starting to push out. So they're finding more and more of these extremely massive, ultramassive black holes that are the centers of BCGs. So there's a survey by Changpei Ma and others called Massive, and they are uncovering this population. So this is the place where I am right now thinking a lot about the modeling. So we have things in course. Yeah, I should stop soon, right?
What's your upper cutoff prediction for the mass?
Oh, it depends. I mean, it depends on a lot of things. It depends on the halo. It depends on the properties of the host halo, on the velocity dispersion of that halo. Yeah, a few times 10 to the 10, sure. Yeah, a few times for the most massive halos. Yeah. So we actually made very concrete predictions, and we were proven right by these guys when they found their first few for particular candidates in the nearby universe. So then the most recent work that we are doing right now, I wanted to stop with where we are right now, because I think this is another nice avenue if people want to go into this field. So this is kind of stuff that has not been done yet. So there are lots of great n-body simulations. Nobody needs to do their own simulation anymore. There's plenty of excellent ones. You just need to mine the ones that are there and start looking for interesting things. Go beyond the low-hanging fruit of what that simulation was made for, to address one particular problem. So here, what I'm showing you is a simulation, a suite of simulations called Romulus. So that one of them is a field box, it's 25 megaparsecs, and the other is the highest resolution ever cluster that has, so there are two, one is a cluster box and there's a field box. And so what you can do, and so this is a hydrodynamic simulation, state of the art, recipes for star formation, feedback, what have you, all the subgrid physics, etc. And so this is a full self-consistent simulation that has slices all the way, it's all done, slices down to redshift 0. So we've been mining this data set and looking at, so remember I told you I made this empirically driven relationship between black hole accretion rate and star formation rate. They're proportional. Is that sensible? I mean, is that what you get in the simulation? Because in the simulations, you are only starting it off with initial conditions, right? You're not tweaking it anymore. It's just you're letting it go, making some assumptions about the recipes. And so here we started investigating, okay, is this valid? Because that's a model that works very well. So is that seen in the simulation? It turns out it is seen in the simulations. So that is this data. This is the black hole accretion rate, star formation rate as a function of redshift for sources in the simulation. So this is for the field box. So these are all galaxies of different morphological types, etc. And this is the cluster box. So these are galaxies that are in the cluster. That's why you have so few of them compared to this. But you see that this relation, the linear correlation between the two holds rather well, okay? And it's not circular. We've not put it in already. We've just made assumptions about how stars form, how the black hole grows. That's a Bondi accretion type model in these simulations. And you get this out, okay? And you can also, like that plot that I was showing you about the tracks of how the black hole grows over time. So these are tracks that I can construct from these simulations. So you can extract and see how the black hole is growing in the black hole mass, stellar mass plane, how the mass assembly, how, and the idea is co-evolution, right? So the big sort of conclusion here is black holes and their hosts co-evolve over cosmic time, okay? And so here we are plotting the tracks to see, so these you see that when you have massive seeds, so this is a simulation in which the seeding has been, initial seeds are quite massive when they start out, because they can't make the seed ab initio in these simulations, right? You put them in by hand, just like we did, right, in our models. So you find that the assembly history is actually quite different, and the punchline is that supermassive black holes and their host galaxies co-evolve, and the seeding, the initial seed determines the growth track of how the co-evolution proceeds, right? And so I'm most excited about LISA. And in particular, I think another area where people have not done enough work, I mean, there's lots of work that's happening now, but I think PTAs, pulsar timing arrays, are, predictions, more predictions for PTAs would be great. So they have a unique sort of frequency, much lower frequency than LISA. But you can still find signatures of supermassive binary mergers in pulsar timing. And so I really recommend, so I think as I pointed out, there are many interesting places where there's a lot of work to be done, and what has been done is simple. And so you can make much more sort of complex models without having to do something very expensive like run a full cosmological simulation. Because these simulations take 17 months to run. So why do you want to start doing them? They're all publicly available. most people have all the data available. So I think the conclusions for now are that, remember I was telling you one of the key things is to try to understand which of these is important. So it looks like if I include all these three processes, obviously black holes grow primarily by accretion. They also grow by mergers. The question is this intermediate thing, how important is that? So it turns out this merger-triggered accretion can reproduce all the observables down to redshift 2, but below that it doesn't. So below that, you actually need a steady mode. You need a steady mode, long-lived accretion. So that is this. Not a bursty mode, but a steady mode that is very long-lived over cosmic time to actually match everything down to redshift 0. Okay. And there are several key observables that are sensitive to seeding. So LISA events, high redshift luminosity functions in the X-ray and occupation fraction, and also, of course, observations with JWST. Well, I think that the combination of these sets of instruments that are going to be available soon will help us sort of disentangle. So we are still working on trying to find if there are any new sort of further observables that we can come up with, observational probes of these models. So this is where we are at the moment. So I'll just stop, and sorry for going over, but I just wanted to wrap up. Thanks very much. Questions?
I understand that the impact of seeding, right? As you nicely explained. What about the impact of feedback? The M-Sigma, the construction is sort of attributed to, to a large part to the the feedback. So both should play an important role, right?
Yeah. So it turns out,
at least in your explanation, that you seem to think that.
So in the schemes that we have implemented, what I call as accretion physics includes the feedback from the accretion, right? And the way these, and the only way in which, because these are not spatially resolved models, right? I'm just modeling the population. So I can't implement different feedback and winds at this or that or the other. All I can do is the way feedback impacts, feedback does two things. It regulates the growth of the black hole, and it impacts the immediate environment, right? It does both. And so I am using only the regulation on the mass growth of the black hole as the way in which feedback comes into the picture. And the way that it has come into the picture is through this index, sigma to the alpha. And alpha being 4 to 5, we expect that that's the range. So what we find is that independent of whether I take 4 or 5, beyond that, it is how I deliver the mass, the accretion, when I say the properties of the accretion model, which is whether the black hole accretion rate is proportional to the star formation rate, or if I just draw from an Eddington distribution, right? So those variables are telling you only how the gas is delivered, right? And that is much more important than the index, than 4 or 5. So one can argue that what is, at least from what this kind of population modeling is telling you, obviously in an individual source is extremely important how the details of the gas, how the energetics of accretion and the feedback couples to the gas, whether it pushes a wind or it does this, that, or the other, right? It's very important when you look at individual sources. When we don't have that kind of detailed data, this is the best that we can do at the moment. And what we find is that if we use the mass growth as the proxy for feedback as well, then what is more important is the gas delivery to the black hole. An assumption about how the gas gets partitioned. When I say delivery, I don't mean spatially either, because these models, again, don't have spatial, right? The spatial understanding is try to see what kind of scaling relations we can actually use in these models. But what we are finding is that the amount of gas that makes it into the hole versus the gas that goes into star formation to gas that is expelled. That is the key thing. That is all we can say about feedback from these models. I think where we will be starting to say more is once we have demographics of the dormant population from that SZ at higher redshifts, then we can say something, because then, those sources are sources in between accretion episodes. So that's a higher level of matching that will be, I know what they are. In my bookkeeping, I know at various time slices, which black hole is on, which one is off, and so on and so forth. I have a census of what they are. But predicting, I can make predictions, but it would be more interesting if we see a few more sources so that I can calibrate a little bit of how long-lived they would be, right? This dormant phase, how long-lived it would be. I need another sort of set of scaling relations, preferably from the data. And that's when I can say more about feedback. Yeah.
Before. The reason, from our sort of toy model, approach is that Deepa has been doing. She's a PhD student. What we found is that if you actually look at an implied starvation of gas after the feedback,
Yeah.
and then that starvation would imply that the index, if it is momentum driven, would saturate at 4, right? So the slopes that you're talking about, whether it's energy driven or momentum driven, whatever the process is, it could be a combination. But once your gas cuts off, right, your slope would be saturating at 4. And that's also the mergers, the probability drops beyond, redshifts of 4, or even it
definitely
drops
2. Yeah.
So there's not much supply. So after that, we just have stellar dynamic feeding in our
Right.
models. So what we
Or
find
mergers.
is that it's sort of,
or mergers, depending on the density of the environment, right? So if you look at a cluster environment, you can grow by mergers.
So when we did that, we find that the P, that is the index that you're talking about, saturates near 4. That's the result we have. And also the constant in front of the M sigma. That's the crucial part. So I think, so you have those two nice diagrams.
Right.
The M star M and the M sigma diagram.
Yeah.
I think it's the co-evolution of this that matters. And I think one last comment is that on all this obviously has an impact on the structure of the galaxy, right? All your fundamental plane relations, in a sense, because the M sigma, the sigma in a Dirichlet's law, you look at it, there is a convolution of these events. So when you're growing the galaxy in your models, which is a co-evolution, you're also growing the galaxy. So I think the star mass and the distribution.
Sure, yeah.
So there's a
but I don't have, in these models, I don't have morphological information about the galaxy or whatever. I'm just looking at the stellar mass assembly. And of course, there are, there are obviously galaxies with bulges, galaxies without bulges, there are spirals. There's an entire sort of a well beyond sort of classes, morphological classes of galaxies. And that kind of understanding of what is happening in an individual source, that you're not going to get from this kind of modeling. But that's not what I was purporting to do anyway, right? So I think that and I think that the idea is that we need these detailed, as I was saying, work like Gulab and Bani showed yesterday. We need these detailed models of sources, not all of which are peculiar. So we need sort of detailed multi-wavelength data of not the freak guys, but some normal, whatever, your garden variety AGN, not things that have extremely massive black holes and so on. Something that samples black hole mass function. We need that detailed modeling. In addition, in order to figure out what is the distribution in terms of the freakiness of properties, so that we can then include them and bracket them for the population, and then see whether you get the right fraction of outliers that you get. So I think these models, you can't push them beyond a point. They are just telling you about the demographics of the population, and they are telling you about, I think what I find very rewarding about this kind of modeling is that multi-wavelength data has been transformative in studying black holes, and now multi-messenger data, hopefully, for supermassive black holes. And so these models allow you to use the wealth of multi-wavelength data as inputs and push and make predictions for as yet undetected populations.
Okay, I think this is a very good place to stop.
Okay, yeah. Happy to chat outside. Yeah.
Yes, of course, I'm sure you have many more questions and comments. And Priya is available today as well as tomorrow.
I'm actually around tomorrow too.
Okay,
Yeah.
so let's thank Priya for this wonderful
Thank you so
lectures.
much.